Okay, guys, topic 3 in special relativity, the Lorentz transformation equations. So we're not going to actually derive these in nitty-gritty detail. It's a neat derivation, but it takes too long. So you're going to have to trust me on this. If you include the constancy of the speed of light, the transformation equations look like you see in equations 3.1 right here. And these are called the Lorentz transformation equations because Lorentz actually got these equations, but the way he did it was not using the constancy of the speed of light. His idea turned out not to be the correct idea, even though he got the right equations. Okay, that's another story in and of itself. And if I see you in person, I can tell you more about it. But anyway, the Lorentz transformation equations you see right there, and those should be compared to the Galilean transformation equations of Newtonian relativity. In fact, if you look, the gamma factor, right, if V is not very big compared to C, which still can be pretty darn fast, the gamma factor is essentially 1. These Lorentz transformation equations actually revert to the Galilean transformation equations, and Newtonian relativity works just fine. So it's only when the gamma factor is significantly greater than 1 that you have to worry about so-called relativistic effects. All right, anyway, so there they are right there. The weird thing is, again, that time is not measured to be the same in the two frames, S and S prime. And in fact, the transformation for time is dependent on X or X prime in the inverse transformation equations. In fact, speaking of those, it's handy sometimes when you go to do a relativity problem that you may need to transform the other way. In other words, you may have to go from S prime into frame S variables. So what you do is you can solve these equations up here in 3.1 for the unprimed variables. But a quick way to do it is just swap the prime and unprimed variables. So I would swap the X prime with the X, put the prime on the T here, and then just make V negative V. So if you do that, you get the so-called inverse transformation equations, which you see right here. So sometimes you need to use those. Just depends on the problem. Okay, now, it turns out that using these Lorentz transformation equations, you can actually get the principle of time dilation that we got in the last video. And I'm not going to go through the details. I'll let you read this, but you can set up a little experiment where you have a proper time interval, that's two events occur at the same position, compare that to a non-proper time interval, and you can actually derive this equation 3.3, which is a statement of time dilation. A non-proper time interval is gamma times a proper time interval. Okay, so a non-proper time interval is longer of the proper time interval by a factor of gamma. You can also do a similar experiment getting length contraction. Okay. Before I get to that, relativity of simultaneity. This is just a statement. There's no big deal here. It's just a statement that if one observer measures two events to be simultaneous, occur at the same time, another observer moving relative to the first observer will not see those two events to be simultaneous. So it's just another implication of time not being the same. All right, getting back to length contraction, you can derive the principle of length contraction equation using the Lorentz transformation equations. However, when you do the derivation, you got to be really careful about how you determine a length. So this is something that I want you guys to remember. When you go to measure the length of an object, usually, right, in our everyday life, we would say, use this algorithm. Measure the position of one end of the object, maybe it's a box, measure the position of the other end, subtract, right? And you got the length of the box. Okay, now that works. However, if the box is moving relative to you, how would you determine its length? And you might say, well, that's just stupid. I wouldn't do that. I know, but let's just suppose you have to, okay? Well, you can still use this same algorithm, but you have to have one additional thing, and that is the two positions of the ends of the box have to be measured at the same time. So really, we need to update our recipe to this recipe. Okay, so to get a valid length, you have to measure the ends of the object at the same time. However, you can relax that constraint if the object is at rest. Then you could measure the end positions at different times, and the subtraction of those positions will still get you a length. All right, if you keep that in mind, you can do a little thought experiment. I'll let you read if you want to on your own time, and you can actually derive length contraction. You can see that right here. In this slide module, I use lowercase l instead of capital L, and I guess I'll say I was too lazy to go and change it to capital L. Anyway, there you go, I admitted it. But there's the length contraction statement right there. A non-proper length is always shorter than a proper length by that factor of gamma. And remember, a proper length means the object's at rest. A non-proper length means the object's moving. Okay? All right, that's it. That's all we're going to do in this module. The next module, we're going to look at velocity transforms. The next video, I should say. Bye-bye.